Alright, so hello everyone. Today we're getting into more linear representation talk here. And we're starting off with sorry, it's taking me a second to get into it here. Starting off with kernels of representations. So we have, I gotta kind of filter, I gotta filter through what they're saying here. So we're going to apply example 4, which this is so hard to read. I think I don't know what they're talking about. So we have that, anyways, we have that the determinant map is a submersion. And we define, why is the notation so like sloppy all of a sudden? Special linearly group of V to be the kernel of the determinant. Which that doesn't seem right. You know what, let's just, this is written really mad. Let's just skip this. They don't even say anything interesting here. It's like 3 sentences and none of it makes sense. Okay, so I have a bad start, but we'll look at stabilizer subgroups. They just went over the previous thing of showing that the equivalent of the kernel of the determinant being your map is the trace being 0. So anyway, stabilizer subgroups. We have, we're doing this in characteristic 0. Then if G acts on X and X is an X, the stabilizer G of X being this element of G in our group that don't do anything to X of X is a group submanifold of G. Now we're going to apply this to representations. First off, let sigma be a linear representation of a Lie group G on a vector space V, and we're going to let V be an element in V. Consider the action of G on V by sigma so the stabilizer of our chosen V is a group submanifold of G, and the equivalent, the Lie algebra of GV, is the elements is of L of G, where sigma bar. I don't know why they have a bar over it. Oh, no, never mind. Of x of v is here. So it's essentially the kernel of sigma bar of x. And to see this, we're going to let v be the map from the general linear Lie group of v to v, sending u to the function u of v. Then the tangent at the origin of v, at the identity rather, of the endomorphisms of v is the map sending y to y of v. So now this is valuation at our chosen v. This isn't, v's, I forgot v was named, these aren't arbitrary, this is function. Since the tangent at E of our group submanifold GV is the kernel of the tangent at E of sigma phi, being the kernel of the composition of TE of phi and sigma, we are done. Secondly, we let f be in the dual of our vector space and consider the stabilizer subgroup G of f with respect to our phi from before composed with sigma, sending G to the general linear Lie group of v star. Then, well, G of f is the set of elements G and G, where f of sigma G is G, and its algebra is the set of elements in the Lie group of the algebra of G, where f composed with sigma is the kernel of f composed with sigma. Now I'm going to show this. For the first, we show that G's inverse is in the stabilizer of f if and only if f of sigma of G is f. As the composition of our star with sigma of G inverse of f being sigma transpose of G inverse inverse of f being f of sigma G. And so we are done by the definition of the stabilizer. And for the second, we show that L of star on sigma of x on phi is 0 f composed with sigma bar of x is 0. We have, and we once again have that L of our star composed with sigma of x of f evaluates to negative sigma bar transpose of x of f being negative f of sigma bar of x. And in this way, we may obtain the affine group AV of a vector space V. We identify everything's glitching. We identify V with the group of translations on V. Then A of V is so essentially the additive group there is the semidirect product, writing letters in the wrong order, the semidirect product of V and its general linear Lie group with a law where V1 and a G1 times V2 and a G2. This can be our first translation plus our G1 acting on the second translation, and then just multiplying our functions, composing the same thing for matrices. Get that sorted, that's good. Alright, so we can identify AV with the subgroup G of GL of V times K of transforms which leave hyperplanes parallel to V invariants by a map sigma from a V to G as sigma of V comma G. Of course needs to on some W and alpha being alpha V plus GW on alpha. G is just, however, it's a group GL of V times K sub F with respect to the linear form F sending V on a K to K by, of course, F of W and alpha just being alpha. Alright, next case, which might be the last one for the day. I don't know how long this is going to take. We let sigma from G to GL of V be a linear representation of a Lie group G in V, and we let beta be an element in the dual space of the tensor of V with itself. We let theta be a map from GL V squared to GL of V tensor V as we saw before. Now we consider the composite representation TAF being theta on sigma times sigma of G into GL of V tensor V. Then the stabilizer in G of beta is the set of G in G, where beta, of course, beta of sigma G times sigma G is beta. It's the Lie group and its algebra. L of G beta is X in the algebra of G. Where beta of sigma bar of X tensor 1 plus 1 tensor sigma bar of X is 0. Which is, this defining condition is equivalent to beta of sigma bar of X on V and W plus beta of V and sigma bar of X on W I don't need that extra bracket, is 0 for all VW in V. And there are two applications, 2G being GLV, sigma being the identity representation, and V being Kn of interest. For A, case A is the orthogonal. So we're going to take beta to be the bilinear form on k to the n by beta of x1 through xn semicolon y1 through yn to be the sum of each x with its corresponding y. The group of elements of our general linearly algebra stabilizing beta is called the orthogonal group. on k to the n, being of course the group, I believe, of the orthogonal Lie algebra. Now we also want to determine g of beta and L of g of beta explicitly. Note that beta u is going to be an endomorphism here of k to the n. So beta of u x and y is beta of x u transpose of y for all u being an endomorphism of k to the n and x and y in k to the n. Then we find for x and y in k to the n. First off, for g in GL of k to the n, I'm tired of saying general linear Lie group whenever I write this out. We have that beta of gx, gy being just beta x and y is equivalent to beta of x g transpose times g times y being beta of x and y. And secondly, for all u in the endomorphisms of k to the n, beta of ux, y plus beta of x and uy being 0 is equivalent to beta of x and u transpose plus u of y being 0. Since our beta is non-degenerate, the stabilizer of beta, our group here, is the elements of GL x to the n, where g transpose times g has to be equal to 1 since x and y can be arbitrary. And similarly, its associated algebra has to be the endomorphisms of k to the n, where u transpose plus u has to be 0. Secondly, we're going to look at the symplectic group. So we're going to take n to be equal to m and beta, the bilinear form. So essentially we're saying we're in an even dimensional space. Of course, it's the symplectic group. We need that to hold of beta from x1 to x 2 of m, which I'm going to write as n. No, I think 2m actually is better in this context. And y1 through y2m to be the sum from... Hang on one second. Yeah, another notational error, that's always fun. Y from 1 to m of xi, y to the m plus I minus x to the m plus I times y to the I. Does not have enough room, but like it's easier to think of these forms, I think, actually as matrices. Like here I should write beta is, I believe this is the matrix 0, in 0, something like that. And I think it could even just be one of them being 0. And here we have beta is like 0, in, negative in 0. Yeah, I think this might just be 0 here, because it's like an x times its corresponding y. Like the first block is x times x, this is x times y times x, y times y. It's something like that. I know there's something like this for the algebras at least. Anyways. Then, of course, G beta is called the symplectic group of our k to the 2m. And we will determine the group and its algebra explicitly. First off, we identify the endomorphisms of k to the m times k to the m with the endomorphisms of k to the n, which is essentially just pairing them up. And from that we can write a linear map u from k to the n as U to be our matrix A, B, C, D, with A, B, C, and D, and the morphisms of K to the M. And from this we define, rather, this is more of an operation than a variable. We find the transpose of such a map to be, well, it's the transpose of D, negative the transpose of B, negative the transpose of C, and the transpose of A. And we do this so that for x and y in k to the n, beta of ux and y is beta of x and u transpose of y. And once again, as beta is non-degenerate, we get on a new page that its stabilizer are the elements of GLNK, GLKN, where okay, they didn't write this as a transpose, they wrote it as a prime. Might as well make my notation consistent with theirs. So anyways, G prime and G needs to be 1 here. And for the algebra, in GL, these are endomorphisms. Should write them as U2. where u prime plus u is 0. Doesn't matter what order you write them in, actually. Which is equivalent, of course. You can see from the above that A transpose plus D will have to be 0. B transpose would have to be B. C transpose would have to be C. And we've only reached half an hour. So let's keep going. Number 4, we can apply this whenever one combines several representations using the basic representation before. We leave this formulation to the reader and instead present an additional example. Let A be a finite dimensional algebra over K and beta B. Now if A transfer A into A be multiplication. Let G be G of A. Then the following are equivalent. These are all for all G and A. Rather for some. For G and A. First off, G is in the stabilizer of beta. G times beta of G inverse of some X in A and G inverse of some Y in A is beta X and Y for all X, Y in A. And likewise, G being splitting it to GX, GY, and in proof of this, we have A is equivalent to B by definition. And B and C by replacing X and Y with GX and GY. Hence, G beta is the automorphism group, is just the automorphism group of our A. We will now show that L of G beta, its algebra, is the space of derivations of A. First off, D being an L G beta is equivalent to saying for all X, Y, and alpha, D of beta X comma Y minus is equal to beta of dx comma y plus beta of x comma dy. I spent 35 minutes, not quite what I would want. And the next chapter is short, so let's do it. Next, it's a section. It's not a chapter. And it is on the adjoint representation. So we're going to let G be a Lie group. And then for each G and G, consider the inner automorphism phi of G from G to G by setting X, just conjugating it by G. They're going to be a pain again. Use multiple variables for the same meaning. Fancy G be the algebra of G, and let 80 from the group to GL of G be the map sending G to the tangent at your identity of the inner automorphism of G. Then the adjoint is a group homomorphism. And we will see that it is analytic. So we consider its algebra version. We will see it is the adjoint from G to endomorphisms of G. Now, since our capital adjoint is a group homomorphism, we only need to show that it is analytic at E to be analytic everywhere. So we will compute it in a neighborhood. So compute it in a neighborhood of E in local coordinates. Now we've seen that phi G of X is X plus G bracketed with X plus higher order stuff, which we write as D, sub alpha and beta. For G to the alpha, X to the beta, where the size of alpha needs to be at least 1 and beta, and the sum of their sizes needs to be at least 3. Hence, the adjoint of G being the tangent identity of phi of G is the map X going to X plus G comma X plus the sum over beta being 1 of our familiar term here on the right. So it's analytic at E. And since we have the restriction that beta has no value of 1, sorry, I gotta move my chair. It's gonna be loud and annoying. Size of alpha must be at least 2. So the tangent at the identity of the adjoint, capital adjoint of Y, is mapped from x to y acting on x as desired. Given that that is just the algebra version. And yeah, we actually made it to our 40 minutes, so we'll call it there. Thanks for watching.